Next equation we want to consider is y double prime minus y equals 3e to the t. This has the property that e to the t is a solution to the homogeneous equation. If we plug in e to the t over here, well, we've seen that e to the t is a solution to the homogeneous equation, that if we plug in y equals e to the t, we're going to get 0. So we can't use a particular solution of the form a e to the t. If we do, the left-hand side is going to be 0, the right-hand side is going to be 3e to the t, and we're not going to have a solution. Well, now, if we try y particular equal t times a e to the t, in other words, a multiple of t e to the t, then this is actually going to work in a way that we'll see. This function is no longer a solution to the homogeneous equation. If we take the derivative and the second derivative, you can verify that we get these two expressions. And our equation then becomes yp double prime minus, that should be yp, equals, well, this solution for our yp double prime, and this expression for our yp prime. Okay? And our equation then becomes this. Again, this is very easily verified. Just plug in these expressions into here, set it equal to e to the 3t so that we're expressing the equation, and this is what you get. And this is easy to solve. We're going to get a equals 3 halves, so that yp of t is 3 halves t e to the t. And it is worth noting that the at e to the t and the negative t times a e to the t subtract off, giving us 0, which simply leads to 280 to the t equals e to the t. In any case, we solve the resulting equation here, and we get 3 halves for the constant a. And you can plug this solution back in to the original equation and see that it does work out that way. This gives us a general solution, which is our solution to the homogeneous equation. So this is our characteristic solution, and here's our particular solution. Now let's consider the more complicated equation where we have two terms on the right-hand side, and instead of just a plain old e to the t on the right-hand side, we'll have a t squared e to the t. If we find a particular solution, which we'll call y sub p1, for the equation y double prime minus y equals t squared e to the t, in other words, the equation that we get if we just omit the cosine t, that might be helpful. If we find a solution y sub p2 to the equation that we get if we leave off the t squared e to the t and just have the cosine t on the right hand side, this might also be helpful. It's going to turn out that if we form our particular solution as the sum of the two particular solutions that we obtain to these two different equations, then that will be a particular solution of the original equation. And the reason is, if y sub p1 is a solution that we can plug into this equation to get the t squared e to the t, and yp2 can be plugged into the equation to get cosine t, then by the linearity of the derivative, what we get when we substitute this solution will be the sum of these two expressions. I'm not going to write that out, but this is a simple consequence of the linearity of differential operators. We won't work through all the details of that, but your text does, and you should certainly be aware of how that works out. Now let's look at the second equation, which is y double prime minus y equals cosine of t. This equation has already been solved. Our particular solution is 1/2 cosine t. For the equation y double prime minus y equals t squared e to the t, this equation, corresponding to this part of our non-homogeneous expression, would be expected to have a solution something like t squared, well, at squared plus bt plus c times e to the t. So do we want to try that? Not quite, because the c e to the t is a solution to the homogeneous equation. We could include this term, but it's going to have to be 0, since c e to the t would end up equaling 0 anyhow. It really doesn't add anything to the homogeneous solution that we already have. We get around this difficulty by trying t times at squared plus bt plus c. That times e to the t. c e to the t is not a solution to the homogeneous equation. In general, we don't want our trial solution to include a solution to the homogeneous equation. So using particular solution yp equals t times at squared plus bt plus c times e to the t, we take the first derivative and had an interruption there, but yp is this expression, yp prime comes out to be this expression, and I've changed the p to a p1 to be consistent with what we have here, yp1 being the particular solution for this particular equation with the t squared e to the t. Then we take the second derivative, and the second derivative will, if you'll take my word for it, turn out to be this. Now we plug this particular solution, the second derivative and the expression for the first derivative, back into the equation. Yp1 double prime minus yp1 equals t squared e to the t, and see what our constants come out to be. We'll continue this in another clip.